So thank you very much for an opportunity to have my first talk in BIMSA. And it seemed to me that it would be nice to have mostly some review of the topic, and then probably we'll hopefully see some intersections with the research interests of the colleagues. And I will state some results, some new results at the end. Sorry, I'll probably turn off the video because we've checked the connection yesterday, and it seems that otherwise there could be some problems.
It was good.
Yes, it is, but sometimes the video doesn't work. So do you see the slides now?
Yes, we see.
Yes,
Okay,
we can see it.
Perfect. So I want to speak about the semi-finite harmonic functions on Bratteli diagrams, and it's joint work with N.Safonkin. Let me very briefly recall the finite group representation theory for the symmetric group. If I have a symmetric group Sn, then as for any other finite group, I will have finite number of irreducible representations. And in this particular case, they will be parameterized by partitions of integer number n into the natural summands. And this partition usually is represented by so-called Young diagram. Namely, if I have 16 as a sum of 7, 5, and 4, then I can write the corresponding Young diagram consisting of 16 boxes with 1, 2, 3, 4, 5, 7 boxes in the first row, lambda 1, second row lambda 2 has 5 boxes, and the third row has 4 boxes. And if I'm interested only in the list of the representations, then I can forget about the structure, and I can use the bijection between the representations and their characters, and try to give the full list of the irreducible characters. Perfect. If I want to speak about the Bratteli diagrams and corresponding locally semisimple algebras, a classical example here is an infinite symmetric group. Now I take not only one symmetric group, but an increasing chain of symmetric groups. I recall that an element of the symmetric group, say S4, can be represented as follows at the sum bijection of the 4-element set. And if I add one more element and map it to itself, then I definitely get have an inclusion of S4 into S5. Reducible representations are parameterized by the Young diagrams. And now I want to represent all the representation theory for the chain of the groups in one picture. Just a second. Yes. So for each level of my graph, I will draw the Young diagrams of the corresponding number of boxes. And also I want to draw the, this will be the vertices of Z plus graded graph called the Young graph. And for the edges of this graph, I want to recall that if I have an irreducible representation of the symmetric group Sn, and I restrict this representation to Sn minus 1, the result will decompose as a sum of irreducible representations with multiplicity 1, and the sum is over all diagrams of size n-1 that can be obtained from lambda by cutting off one box. Namely, if I take this lambda and restrict it to the previous level, I will have a sum of 3 irreducible representations that represent diagrams when I cut off one of the 3 boxes that are marked with a red dot. And now I take any vertex and I draw the edges to the previous level if I have the corresponding components in the restriction of this reducible representation. This is the construction of the Young graph when I start from the chain of finite groups. And in effect, I can almost reverse this construction. Let me recall that if I have a finite group, if I'm interested only in the representation theory, then I can consider the group algebra instead of group itself. A group algebra of a finite group is always semisimple. That is, it is a direct sum of full matrix algebras, and it means that it is fully determined by the sizes of this matrix algebras. In our case, the sizes of these matrix algebras are just the sizes of the corresponding irreducible representations. Now, if I have only the graph, let me consider, for example, this red vertex. By the definition of my restriction, I can restrict myself to the previous level to get 2 irreducible representations of S3. For the left one, I have no more branching. It means that this irreducible representation is one-dimensional. For the right one, I have branching into 2 diagrams on the previous floor. And it means that actually this representation is 2-dimensional, this is 1-dimensional, the dimension here is 3. And in general, what we get, we can now define the dimension of the corresponding vertex combinatorially, just as the number of paths from the top of my graph to a particular vertex. And we see that we have 3 paths from the empty diagram to a fixed diagram here. Now, once again, we can ask the question about the representation theory of this locally semisimple algebra. The question of all irreducible representations is wild in a sense that there is no hope that we will actually get a reasonable answer for this question. So we should restrict ourselves to some particular class of representations. And one of the classic questions for this particular algebras is to restrict ourselves to so-called 2 one-factor representations, with a finite trace. These are exactly the representations that are in a bijection with the corresponding characters of the infinite symmetric group. The definition is slightly different. Here it is. I say that a character and chi is a character if first it is central, chi of AB is equal to chi of BA. Second, it is non-negative. Chi of A star A is non-negative, where star is a standard involution for the group algebra. And we would like to normalize it. So chi of 1 will be equal to 1. We have a function on, say, S infinity, and I want to represent a character on the Young graph. How can I do it? Let me restrict my character to nth level. it's easy to see from the definition that what we actually get is a sum of irreducible representations of the characters of the irreducible representations for the group Sn with some non-negative coefficients, because our function is non-negative, and with some normalization. We can do it for any level. We can do it for nth level. We can do it for the level n-1, but we can do it in two different ways. If we restrict ourselves to the nth level and then to the level n-1, definitely we get some relation between the values of my function h on these two levels. As we define the edges by the restriction, it's easy to see that what we actually get is that the value of the function at a particular diagram should be just the sum of all the values of h for all the diagrams mu that are obtained by adding one box to my fixed diagram lambda. So this leads to the corresponding definition. I will consider functions from my Young graph to non-negative reals, normalized at the top of my graph, such that for any vertex lambda, corresponding value is equal to the sum of the values of all the immediate descendants. If this is true, I will call my function harmonic. So I will be interested in non-negative normalized harmonic functions, but I will omit non-negative and normalized and just call them harmonic functions. And I will define them, I will denote them by h finite. And there is another way to look at characters, namely I can consider so-called central measures. I don't want to give you the precise definition. Let me just describe you what do I mean on the picture. I want to have a measure on the space of paths of the Young graph. It is sufficient to define the measures of the cylinders. Namely, I fix some beginning of the path and I consider all the paths that with a fixed beginning. If I know the measures of all the cylinders, definitely I know the measure itself. Now I fix a vertex, say the red one, and I consider two cylinders that are defined by the finite paths ending in the same vertex. In general, their value can be different. But I want to define a central measure. I will say that for any initial path ending in, say, this particular vertex, the measures of all the corresponding cylinders will be the same. This means that actually to define the measure, we only need to define a function on the vertices of my graph. That is the measure of any of these cylinders. And it's easy to see that, for example, if I have a measure of this cylinder, it's definitely the sum of the measures of all the diagrams obtained from this one by adding one box. That is the corresponding harmonic measure is definitely, the corresponding function is definitely harmonic. And this actually means that we have a bijection between the set of all normalized characters, the set of all finite harmonic functions, and the set of all central measures on the paths of my graph. So I have at least 3 languages to describe the picture, and I will mostly use the language of the harmonic functions. And one more remark. We have Choquet's theorem. Once again, I don't want to write an explicit statement. All I want to say is if we're interested in, say, functions, in our case, it's sufficient to speak only about the extremal harmonic functions. If we know all the extremal harmonic functions, this is the notation for the extremal harmonic functions, then any other normalized harmonic function will be just some probability measure sitting on the set of all extremal harmonic functions. So from now on, we restrict ourselves only to the extremal harmonic functions. For example, coming back to the Young graph, the question, what are the extremal finite harmonic functions for the Young graph itself? It was solved more than half a century ago. It is famous Thomas theorem. And what we have as an answer, we have an two infinite sequence of non-negative parameters alpha I and beta g, and an additional parameter gamma, with the only restriction that the sum of all these parameters is equal to 1. Thomas, his question and his way of proving the corresponding theorem was quite analytical, and later this theorem was revisited numerous number of times. There is a famous statement of Thomas theorem and some adjustment of Thomas theorem due to Vershik and Kerov. It says that we can, when we restate the corresponding equation in terms of central measures, and if we fix alphas, betas, and gammas, and we're interested what is the support of this particular central measure. Central measures are sitting on the paths of the on the Young graph, that is on the growing Young diagrams. We add boxes to Young diagram one by one. And the answer is that a central measure that corresponds to the fixed parameters alphas, betas, and gammas can be represented as follows. Our growing diagram should have the following frequencies when our diagram grow to infinity. Let lambda n be the nth vertex on my path. Lambda n1 will be the length of the first row, and the proportion of the box sitting in the first row should tend to alpha 1. The proportion of the number of boxes sitting in the second row should tend to alpha 2, and so on. And the same for the columns. That here we should have the frequency beta 1 for the first column, the frequency beta 2 for the second column, and so on. This is the type of answer that we often get when we ask the questions about the harmonic functions on Bratteli diagrams. And we've seen the Young graph. Let me give you the general definition of a Bratteli diagram itself. So a Bratteli diagram gamma, or a Z plus graded graph, it consists of the vertices that are graded by Z plus, and the edges can be only between the adjacent levels. If I have a vertex in gamma n, then often it's convenient to think about the directed graph and directed edges. Then we have all the edges from gamma n to gamma n plus 1. And one more important property, there should be no hanging vertices, in a sense that if I have a path from the top to a fixed vertex mu, then I can prolong it to the next level. There is some immediate descendants, and it means that there is one more immediate descendant and so on, and every path can go to infinity. There are two additional properties. First of all, it is usually convenient to take finite levels, and the classical theory of Bratteli diagrams, there we usually use the finiteness of the levels, but it's also possible to think about even the continuous levels. Last years, there are some new results that this one is useful but can be omitted. And the second property is vice versa. If I have a vertex, usually it's possible to find a way from any vertex of the graph to the top. This one can be omitted with some additional technical issues, but it is often the case, so we often imply that we actually do have this property as well. When I have a general Bratteli diagram, once again, I can define the combinatorial dimension of my fixed vertex lambda just as the number of paths from the empty diagram at the top of my graph to my fixed diagram lambda. And once again, I can construct the semisimple algebra that corresponds to nth level just as a direct sum of the corresponding full matrix algebras. And the edges between the nth level and the n plus first level, they define the inclusion of the algebras. It means that I can construct the sequence of semisimple algebras, and I can consider A infinity as the corresponding inductive limit. This is by definition the locally semisimple LS algebra. And if we're in a category of C-star algebras, then the corresponding limit is called approximately finite or AF algebra. Now the question of the finite characters or harmonic functions on Bratteli diagrams is quite well researched. There are dozens of results. And if we generalize to semifinite harmonic functions, then actually the definition is not new, but until very recently, there was just not much attention for this particular question. To define semifinite harmonic functions, first of all, let me recall that we say that I is an ideal in my graph if all the descendants are included, if some vertex is included to I. And we have a co-ideal if all the preceding vertices are included. Let me show you the picture once again. So if I take the red vertex once again and I think of the union of all the vertices of the path from the top to the fixed vertex, then what I get is so-called principal co-ideal corresponding to this vertex. And vice versa. If I fix once again this vertex and I consider all the vertices on the path from my vertex downwards, then the resulting union is the principal ideal corresponding to this vertex. Now back to the definition of the semi-finite harmonic functions. We want to allow some infinite values. Let me first give you some non-example as a motivation. I take H, a finite harmonic function, and I take some co-ideal. Then obviously I can define a function Hj, just allowing infinities for my co-ideal J. But actually, this is not an interesting way to construct a new harmonic function, because what we actually get is just a pair of a harmonic function and a co-ideal. We want for all the infinities to appear in some natural way. What do I mean by natural way? I have a harmonic function H. It is by definition the sum of the values of all the vertices that are adjacent to mu on the next floor. I can iterate this procedure, and I can take gamma where n is gamma n, where n is some big number, and then what I actually get is the sum of all the values of my function on that level gamma n. And it's easy to see that what we get as multiplicities is the number of paths from lambda to mu. This is, I just restated the definition. And now I want to say that my function is semi-finite. If I take this sum, but I look only at finite values of my function h, and then I consider the limit when n goes to infinity. What does it actually mean? For finite values h lambda, this is an obvious equality even if there is no limit. Then if I restrict my attention only to the finite values, to the ideal of the finite values, of course, this is the lower bound for any value here. And what I actually want is, I actually want that all infinities appear as some limit of the corresponding sums of the finite values. In other words, I have some natural way to extend my harmonic function from the ideal of finite values to the whole graph, and I obtain all infinities only in this fashion. And in fact, I can define much more powerful extension. For extremal harmonic functions, it turns out that it is sufficient to have a restriction to any ideal on my graph. Here is the proposition. I take a harmonic function, an extremal one. I take any ideal in my graph. Then I can extend uniquely harmonic function from this ideal back to the whole gamma in the following fashion. The value of my harmonic function at some point lambda will be just, as we've done it before, the limit of the corresponding sums when I take the finite values of h, and I restrict my attention only to this fixed ideal I. And it's not that hard to see that actually we get a bijection between the extremal harmonic functions with non-zero restriction to a particular ideal and the corresponding harmonic functions on the ideal itself. So this will be one of the powerful tools that we'll use to describe the semi-finite extremal harmonic functions. Now, to get used to the definitions, let me briefly show you how can we find the semi-finite harmonic functions in the baby example of the Pascal triangle. First of all, let me recall that I can assign zeros to the left edges of the Pascal triangle and ones to the right edges. And then if I take any path in the Pascal triangle, actually it will be uniquely represented as a one-sided sequence of zeros and ones. And now we know that the question of the harmonic functions is the same as the question of the central measures. What is the central measure here? Let me fix, say, this red vertex. I have 3 paths from the top here. All the paths that start with this particular path are 0, 0, 1, something else. All these paths are 0, 1, 0, something else. And all paths in this cylinder can be described as starting with 1, 0, 0 and something else. And we see that if we speak about the central measures on this particular path space, this actually means that we allow the permutation of the coordinates. And it's easy to see that for any particular vertex, it's the same condition. And actually, this is a bijection of these 2 particular sets, the set of the central measures on the path and the set of so-called exchangeable random sequences of zeros and ones, random sequences of zeros and ones that are invariant under the permutation of finite number of coordinates. And the question of the exchangeable random sequences is also known for a very long time. It's called in this particular, it's called in general definitive theorem. And in this particular case, definitive theorem tells us that if we speak about the extremal, say, central measures or harmonic functions, for the extremal central measures, they are given by just the Bernoulli sequences. Of course, if I have a sequence of independent trials, they're invariant under the permutation of finite number of coordinates. But it turns out that there are no other extremal measures or sequences of this kind. Nice. I've described you the finite harmonic extremal functions here. How can we find the semi-finite ones? Let me find some lambda on the highest possible level of my graph, such that h of lambda is finite. Then by definition, for one of the neighbors, for one of the parents of my lambda, let me define it, denoted by lambda prime, the corresponding value is infinite. And for simplicity, let me normalize my character so the h of lambda is equal to 1. If you remember the proposition on the previous slide, when I restrict my attention to this particular ideal, first of all, as the vertex is finite, all the values in my blue ideal are finite. And this particular value is infinite. And it's easy to see that it means that on this side, all the values are infinite. And now, to be semi-finite, I need this particular infinite value to be a limit of the corresponding sums of finite values. I can restate my definition as follows. I take n somewhere. Then I consider all the paths from the vertex lambda prime to all the vertices mu on that particular level. And I sum up all the values of my function h, where the sum is over all the corresponding paths. Now, if I consider the paths from lambda prime somewhere inside this triangle, then I should add a path through this edge, or through this one, or through that one, through exactly one of the edges marked by a red arrow. And it's easy to see that if it is this particular edge, then when n goes to infinity, we obtain exactly h of lambda here. That is the corresponding measure here will be equal to 1. And now we are thinking about the extremal semifinite harmonic function. We have a proposition on the previous slide. Then when we restrict ourselves to this particular triangle, we get also an extremal, now finite extremal harmonic function. We have just described them. They are Bernoulli measures, and that is there exists a p such that the restriction to this particular triangle corresponds to some p. It means that I have the probability of, say, 1 here, the probability of double ones here, the probability of triple ones here, and so on. So here the value is p, here the value is p squared, and here the value is p cubed, and so on. And then if I take all the paths that go through this particular edge, in the limit I get the value h of lambda, which is 1. If I consider all the edges, all the paths that go through this edge, in the limit I get p. For all the paths that go through this particular edge, I get p squared, and so on. Adding up, 1 plus p squared plus p cubed, I get 1 over 1 minus p. And this is the value of h of lambda prime. And I know that the corresponding value should be infinite. It means that p should be equal to 1. And if not this parent but this parent is infinite, then vice versa, p should be equal to 0. In any case, we see that if we speak about the semi-finite harmonic functions instead of finite harmonic functions, then it is often possible to restrict ourselves to some ideal of finite elements, and therefore we will have some similar problem for the finite harmonic functions. And moreover, often we have some degeneration. Let me describe you the answer in different terms. Now, if I speak about the Pascal triangle, we can embed the Pascal triangle into the Young graph. Namely, this is the diagrams which have only one column and one row. And we can add one box to the first row, or we can add one box to the first column. If we add to the first row, we get to the right. If we add to the first column, we get to the left. How can we describe all the extremal harmonic functions semi-finite for the Pascal triangle? First of all, we can describe the corresponding kernel that is the part of the Pascal triangle where the values are 0. Usually it's more convenient to describe the support of the measure, that is the union of all diagrams where we have non-zero values. In this particular case, the answer will be as follows. We will have some finite number of boxes, say, in the first column, and we have an infinite number of boxes in the first row. We will define the corresponding union representing my support by lambda infinity. And it's also convenient to denote this finite part by, say, lambda f. Then useful way to write the corresponding semi-finite extremal function is we will have zeros if we're not sitting inside the support. We will have infinities if the corresponding finite part is not filled with boxes. If there is at least one empty box here, then we're in this case, and we will actually get infinity. And only if the finite part is filled with boxes, then we will have some non-trivial value. Well, for Pascal triangle, everything is highly degenerated, and we get only one here. So this was the picture for the Pascal triangle. And to see the picture for the Young graph itself, we need a couple of additional definitions and propositions, namely, once again, a principal co-ideal gamma lambda for a fixed vertex lambda is just all the vertices that are above my fixed vertex lambda in sense of paths. So, for example, if I take this one, that this will be the corresponding co-ideal. And it turns out that if I want to characterize all the extremal functions, first step is to understand what are the possible supports of the function. And it turns out that it always can be defined by some paths. If we speak about the Young graph, for example, what is the corresponding principal co-ideal? It's just I fix a vertex, and the corresponding co-ideal is all vertices, all diagrams that are inside my fixed diagram. Now I have a path. I have a growing diagram, and I consider the union of the corresponding principal co-ideals. What does it actually mean? It's actually mean that I just consider the union of all these diagrams, and the support is just all the diagrams that are inside the corresponding lambda infinity in general case. Now, how can we describe the corresponding infinite diagrams? First of all, if we have infinite number of rows that grow to infinity, we will definitely get the whole Young graph. If we have finite number of rows that grow to infinity, say k, and finite number of columns that grow to infinity, say L, then we can actually get two kinds of pictures. We can get either this kind of picture, when we have k infinite rows, k infinite columns, and nothing else, or we can get L infinite columns, k infinite rows, and some finite addition here. Up to this point, all the propositions were quite general. It's in general possible to restrict our extremal harmonic function to a particular ideal and then characterize the harmonic functions on this ideal and then lift everything back to the graph itself. This is a general proposition. Also, we can, in general case, describe the support of an extremal harmonic function as the corresponding union of the diagrams in some general sense. And now I want to present you the proposition that is quite restrictive. Namely, I will need to use the fact that the Young graph is multiplicative in the following sense. I take the symmetric functions. I can, inside the symmetric functions, I can take a basis of the Schur functions. And I can grade the Schur functions by the number of boxes of the corresponding Young diagram. Then essentially, my symmetric functions they have a basis that is parameterized by the vertices of the Young graph. So the vertices are defined, and now I have a distinguished element P1 that is just the sum of the coordinates. And we have a Pierre rule. The Pierre rule tells us that if I take a Schur function as lambda and multiply it by P1, the result is the sum of the Schur functions for all the diagrams that are obtained from the initial diagram by adding one box. So it's the same definition as for the induction of the representations of the symmetric group. And it means that this multiplication by P1 defines the edges of the Young graph. So I've presented you an algebra of symmetric functions, where the basis represents the vertices, and there is a distinguished element that describes the branching of the Young graph. Well, by definition, this is when we call the graph multiplicative. And it turns out that if we restrict ourselves in a proper way to the L columns and K rows, we also get a multiplicative case. So the Young graph itself and this second case are both multiplicative. And now an important proposition is if I have a multiplicative graph and there are no zero divisors, then it's not possible for the semi-finite harmonic function to be non-degenerated. In multiplicative case, semi-finite harmonic functions are always degenerated. And well, it means that if we're speaking about the support of the semi-finite harmonic functions, this case is not possible, this case is not possible, and this is the only case that is essentially allowed. Let me draw it here once again. Now we know that this infinite diagram represents the support of our semi-finite harmonic functions. It means that we can forget about the rest of the Young graph and think of this co-ideal as just a graph. Now we consider only the Young diagrams that are included in this particular infinite Young diagram, nothing changes. Now we have a proposition that we can restrict ourselves to the ideal of our choice. Here is the ideal. I fix lambda f, and I consider the principal ideal generated by lambda f. We know that it is sufficient for us to describe all the irreducible, all of the extremal harmonic functions for this particular ideal. And then we'll extend everything back. But now, if we have this particular ideal, here it is, it's called here J1. Principal ideal means that lambda f is here, and we've agreed that we consider only the diagrams that are inside our lambda infinite. Now, I have a picture on the right as well, and please shrink lambda f to the smallest possible rectangle to obtain mu f on the right picture. If we restrict ourselves to this J1, it's almost immediate to see that we actually have a bijection. So this we get two isomorphic graphs. The graphs that are the ideal that is generated by lambda f on the left is isomorphic as a Bratteli diagram to the ideal generated by mu f here, because we can only grow inside these k columns and this L, this k rows and this L columns here, and the same k columns and the same L columns there. So the questions of the extremal harmonic functions here and the extremal harmonic functions are the same. It is stated on the previous slide that for this particular graph, there are no strictly semifinite, how to say, semifinite and not finite harmonic functions. So only finite harmonic functions are presented here. That is, and we know them. The finite harmonic functions are described by the Thomas theorem from the beginning of the talk. As we know the harmonic functions for all the Young graphs, if we restrict our attention to these particular diagrams, of course, it's just a particular case. So this is a simple particular case of the Thomas theorem. We have frequencies of rows and frequencies of columns that fully describe the extremal harmonic functions here. We lift them up back to this ideal via this isomorphism. And then we have a proposition from the first part of the talk when we can lift everything back up from an ideal. And this means that actually these two jumps give us the characterization of all semifinite harmonic functions on the Young graph. Well, here is the result. It was initially proved by Vershik-Kerov, and what we've just seen that we should first fix some L, K, and non-trivial lambda f here, and also for each row and for each column, we should have some frequency alpha of beta, and sum of alphas and betas should be equal to 1. And once again, the corresponding harmonic function is defined as 0 if we're out of the support, if is infinity if we are not inside our principal ideal, and here we have some formula with the use of the Schur functions. The initial proof of Vershik-Kerov on this theorem, it was by so-called ergodic approach. In short, if I want to understand what are the values of the harmonic function, of an extremal harmonic function, I can take the corresponding skew dimension, the number of paths from my fixed vertex lambda to some faraway vertex mu n, normalize it by the total number of paths to mu n. And for almost every path with respect to the corresponding central measure, we remember that there is a bijection between the harmonic functions and central measures. For almost any harmonic paths with respect to the corresponding central measure, this limit gives us the harmonic function itself. And it means that if we're interested in the list of the extremal harmonic functions or the corresponding characters, we should understand when do we have this limit for all the vertices. And it turns out then if we speak about semi-finite harmonic functions, there are often some technical difficulties. There were some technical difficulties even when this article was published long ago. And it turned out that the method that I presented you today, so-called Wassermann's method, it goes back to the work of Wassermann on the Gelfand-Zetlin graph for the unitary group. It is much more simple and natural tool. We think of the possible supports of our functions. Then we find some nice principal ideal of finite elements. We restrict ourselves we restate our problem to the problem of the description of finite extremal harmonic functions on a graph similar to the initial one. Then we solve this problem and we extend everything back to obtain the result for the semi-finite harmonic functions. But there is a catch, maybe even two. One of them is that, for example, we at the moment don't know how to avoid this use of multiplicity. For a list of interesting graphs, we do have the multiplicity property. But nevertheless, it's really nice to have a general tool to solve such kind of problems. And if we speak about the Wassermann's methods, well, I can't say that we do really have it. And ergodic methods is extremely general. So this here I have the statement for the finite harmonic function, but we have similar statement for semi-finite functions as well. Some words about our work with Nikita. So this was our one of our main motivations. We know how to use Wassermann's methods, but we want to have at least some examples where we can use mostly ergodic approach, or well, exclusively ergodic approach if possible. Here's our example. So instead of infinite symmetric group, I want to consider infinite inverse symmetric semigroup. So symmetric group itself is a group of bijections of a finite set. Now let me consider, instead of bijections of a finite set, partial bijections of a finite set. For example, I have a set of 4 elements here, and I will say that, say, 3 of these 4 elements are mapped somewhere, and the 4th is mapped nowhere. Once again, representing the bijections by pictures similar to the symmetric group case, we can easily see how we can multiply them. We get a semigroup. In fact, it's easy to see that flip is a nice involution. It means that we actually have an so-called inverse semigroup. That's why the corresponding semigroup algebra is once again semifinite. The corresponding group algebra, once again, we represent it as a direct sum of the full matrix algebras. And for the corresponding chain, we can write the Bratteli diagram. The Bratteli diagram looks like this picture. We have the Young graph on the right. And to draw the full picture, the simple way to understand what's going on is as follows. Start with empty diagram. And next, you can either add one box, as usual for the Young graph itself, or do nothing. Add one box, or do nothing. You have two possibilities. And we see that, first of all, this is some general procedure. You can take any Bratteli diagram and speak about the corresponding slow graph. When we first studied these graphs with Professor Wershik, we called them slow graphs of Pascalizations, because we see that there is a structure quite resembling the Pascal triangle itself. So this is the resulting Pascalization of the Young graph. Or also there is a natural construction. If I have two Bratteli diagrams, I can speak about the product of two Bratteli diagrams. And in a sense, this picture is a product of the Young graph and natural numbers represented as the simplest possible Bratteli diagram, just a half line. Okay, nice. Let me, it's 6, just as a final point, let me show you one of the results of our work with Nikita. If we want to describe the semifinite, finite or semifinite harmonic functions on the corresponding Pascalization of the Young graph, then let me probably come back. I didn't tell you. So when we speak about the Tama theorem, the description of the corresponding harmonic functions are by the frequencies of rows and by frequencies of columns. And if we speak about the Pascal triangle, then, well, we have P is actually the frequency of, say, the first row. In our case, if we have a combination of a Pascal triangle and the Young graph, it's reasonable to expect that in general case, we'll have one additional frequency. Namely, if we want to describe the support of the corresponding harmonic functions, we should expect the frequencies of the rows, the frequencies of the columns, and also the frequency of adding a box. Right, in sense of the Pascal triangle, we have, say, the frequency of adding ones moving to the right. And it is really the case here. The first part of the extremal semifinite functions is parameterized by alphas, betas, and this additional finite part of the Young diagram as in the case for the Young graph itself. And we have an additional parameter P that corresponds to the frequency of adding the boxes. And we have two generalizations when we either if we come back to the Pascal triangle itself, then, well, they in a way correspond to the generalizations of the Pascal triangle itself. We either start somewhere and add the boxes as quickly as possible, or we start somewhere and we do not add the boxes at all. We have different description for these two cases in a general setting, but at first glance, the description is more or less the same. And we also have with Nikita a classification of the semifinite harmonic functions for the case of the general product of two Bratteli diagrams, but, well, they are known as pictures, so I don't want to present it here. Thank you for your attention.
Thank you for your talk. Any questions, comments? Yuri, maybe you?
Hello. So I have one maybe stupid question. Why do you exclude 0 in case 1 of this slide, p equals 0? So
yes, nice observation. So you see, we want to combine the representation theory of the Young graph with the representation theory of the Pascal triangle in a sense. But if P is 0, if we do not add the vertices, right? So it just means that we take some vertex and then we sit in this vertex forever, more or less. It means that actually there is no asymptotic representation theory of the Young graph itself involved. But if we add boxes, at least with some flow, with P non-zero, then actually we will eventually get an infinite Young diagram, and this means that we will have all the theory of the Young graph itself involved. Sounds reasonable?
Yes, but well, I'm a bit confused why it can't be such degenerate component with p equals 0 in some mixture, but maybe.
Ah, sorry, I didn't get your question. All I wanted to say is that it's not a convenient way to write it. If I put p equals 0 here, then, well, we get 0 almost all the time. So it will be this case, right? The result will not depend on H alpha beta. This is all I want to say.
Oh, okay. Yeah. Thank you.
Thank you. One more question, comments? Okay, thank you, Pavel. He was the first speaker from BIMSA, so it's very nice to us. Okay, let us finish our seminar. I will wait slides from Pavel. And next, yes. No, okay. And the next speaker will be, oh, sorry. Okay. The next speaker will be Professor Naomi from Japan.